Have you been enjoying yourselves? Yeah. I have too, and as much as I would have loved to keep sitting at the back of the room and listening to their talks, they made me come up and actually do some work too. So I'd like to tell you about something that is the sort of, let me put it this way. How many of you are familiar with Bruce Schneier's most recent book, Secrets and Lies? Wonderful about data security, not just crypto, but security in the modern world. Well, Scott has just told you a bunch of lies. I am now going to tell you about some secrets. And the reason that you do not have the handouts for these talks in your printed handouts or in the PDFs that you received is because it would take all the fun out of it. I have got innumerable emails. Leor just came up again. People have been guessing, what are the keywords? Nearly all the guesses have been wrong. I gave you a hint. The two keywords that have changed fundamentally in C++11 and almost nobody has noticed have nothing to do with auto or register. No, it's not static. It's not virtual. But let's see what they are. Because we made a lot of changes in C++11, and it only occurred to me around the winter time, this past winter, when I was at a customer site working with some friends, that we started having a discussion that made me realize, wait a minute, of all the lists of things we did in C++11, we actually changed something that I don't know if we knew we changed. Now, I don't want you to get the idea that means we don't know what we're doing. It just means there's a little something extra, and it's actually goodness. Let's talk about these two related keywords. Let's always start with code. So take a look at this code, and the header stuff is grayed out. The key parts are the 4 main lines. I've got a vector int, which is some size I populate. I'm going to launch 2 async operations and then wait. Each async operation is simply going to create a local pair of int and vector int, initialized with either 1 or 2, and then a copy of that vector. Notice I don't have to capture anything in the Lambda because that's not a local, it's a global object. So that's why there's no need to say equals or ref there. It's as good as ref. And then I wait for the lambdas. First question I have for you, is this a legal, as in correctly synchronized program? I'll give you that it compiles. Is it a legal, correctly synchronized program that doesn't have race conditions in it? Anyone? Oh, don't be shy. It's near the end of the day. Yes. So you would say that yes, it's correctly synchronized because the vector is statically initialized. It happens to be. Well, there's some dynamic initialization because we're doing some allocation, memory allocation, but it is initialized nicely before we start main. And we're reading from it. Anybody else? There was another hand. It's only reading the vector, right? It's initializing. Yeah, it should be fine. Just here with Christopher. Okay, so how many of you, let's take a show of hands and we'll come back to this. How many of you would say, yeah, that looks like a correctly synchronized program? How many of you are thinking, he wouldn't be putting this up if it was? We'll come back to that. Now, take this code and make one little change, because so far I've only talked about standard types. You write types too. You write types, if you're Scott Myers, that are named widget. And because I'm going to be a little more conformant to the standard convention, mine are lowercase. So I'm going to create a class widget. I'm going to create 2 objects, W1, W2, of this type widget. And this is a complete compilable program that I'm just omitting the details of class widget and what it might contain. But I'm going to do the same thing. I'm going to launch 2 async operations. Each one of them is going to create a pair of widget and widget that takes a copy of W1 and W2, and then I join. I have 2 questions for you. The same as before, is the program correctly synchronized? And then also, what can we say about the thread safety of class widget? Discuss. There's a hand at the back. Go ahead. The copy constructor has to be thread safe. The copy constructor of what? Of widget. Says who? You do. So you are going over to that author of widget and you are saying, now listen here, buddy, if you had better have made that thread safe, that's the kind of conversation you have at work. That's good. That's good. It's important to be tactful but firm. All right, anybody else? Okay, how many of you would like the answer to question 1 to be yes? How many of you would like it to be yes? Okay. And is there anything anybody else wants to say other than, I hope it's thread safe, about the answer to question number 2? Keep this in mind because, I mean, look, we're experts. Most of the people in the room have scads of years of experience in C++. I'm talking about a simple 4-line program, and we're like, well, sort of squirming in our seats. Let's dig in. Now we'll dig into the meat of it. What does const mean in C++ 98? So if you've got people who are coming to C++, they're interns coming out of school, they're refugees from other languages, and you're teaching them what const means. So what are some frequent misconceptions, and what does const actually mean? Anybody? It's a hint, Alan says. Okay, anybody else? It's promise. Oh, yeah, that's sort of like if the other side of a future? No. Okay, and it's specifically, what do people often think it means, but what does it actually mean? What word would you use or phrase to describe? Immutable. So people would think it might be immutable, and it actually means, what do we teach? Immutable through that, now do you mean bitwise immutable through that view of it? Logically, there's the word. We've taught a generation, or two, depending on your length of generation, of C++ developers. Const means logically const, not physically or bitwise const. How many of you have been pretty familiar with that? Right. You don't know const. The meaning of const is fundamentally different in C++ 11, and I, for one, didn't realize it until after we shipped the standard. And when I've asked only a couple of people. One of them was Hans Bohm, who leads the concurrency subgroup in standardization. And after a couple of emails back and forth where he said, no, he said, oh yeah, I guess so. So let's see what so means. I have 2 quotes from the standard, one from the standard language and one from the standard library. The one from the standard language is in section 1.10, right near the front of the standard, where you want to know things about the basic safety of your program. In particular, you want to know if a program is thread safe, if it is well synchronized. And to do that, you have to define what a data race means. Now, leaving aside C++ for a moment, the usual way we say what a data race is you say you have the same object or memory location, 2 threads are able to access it unsynchronized, and at least one is a writer. Because if they're both readers, I mean, you can just be reading those bits all day long and it's fine, but at least one is a writer. That's what we say in all the other languages. What we say in the C++ and, I believe, C standards, because the C standard followed the C++ memory model, in 110 paragraph 4, 2 expression evaluations conflict. That's what we're looking for. If one of them modifies a memory location and the other one accesses or modifies the same memory location. So if at least one is a modifier. The execution of a program contains a data race if it contains 2 of these conflicting actions, which we've just defined, in different threads, at least one of which is not atomic, because atomics are synchronized, they get a free pass, and neither happens before the other, so they could be concurrent, they're not synchronized. Any such data race results in your best friend and mine, undefined behavior. What is one word conspicuously missing from this entire section 1.10? Const. We say modifies. We even say modifies a memory location 1.7, but that just tells you what the memory location is. It doesn't say what modified means. Now, you and I, we all know what modified means, right? It means right over the bits of somehow. We don't say that really anywhere. But wait, because this is only half the story, because this is the standard language rule. There is a section in the standard library introduction which describes the thread safety of the standard library and all types you use with it, including yours. And it refers back to section 1.10 here, and it defines what modified is. And it has some of the same things. It refers to 1.10. It has the word data races. It has the word modify. And the most important word, which appears only once in this whole section, is what? See if you can pick it out from the slide. So to prevent data races, so clearly we are talking about that, about the memory model and data races. We are defining what modify means. Look, there's another hint. By the way, we really mean the modify, the word in 1.10. We, the standard library working group, say that for our standard library and all your types you use with it, which are plenty, none of our functions shall directly or indirectly modify objects accessible by threads other than the current thread, so any shared objects, unless the objects are accessed directly or indirectly via the function's non-const arguments. The standard library makes it very clear that they take the view, the stand, that const means read-only, does not change the bits of. This is a first. And it has some interesting consequences because it's not just the standard library's own types, it's anything you instantiate it with. So from that point forward, if you go forward now to in the standard library, the very next case I could find where you mention a type that could be instantiated with some of yours are these functions that do additional relational operations. They're the ones that if you provide only less than and equality for a type, it generates the others, the other four. And notice as it defines them, it takes for instance, the inequality operator takes a const reference or a reference to a const t and a reference to a const t. And it's defined to say it calls the equality operator and returns not that. So not only must the equality operator be a const function, but what else? So what? What does this imply about any type you use with relops? What must be true? Must not mutate the bits. And let me be even crisper. Every type you could possibly use with std_relops is required to support thread-safe equality comparison. That means either it reads only the bits or it is internally synchronized, but it has to be thread-safe. So it could be that it just doesn't ever modify any of the bits, which is fine. Or if it does, it had better synchronize it. But it has to be thread safe. Now, some of you may be saying, relops? Really? Like, how many of you use relops every day? Right. It's in there because Alex Stepanov had it in the HPSTL. It seemed like a good idea at the time. Then it came into the standard. It kept conflicting with everything because it turns out you already define those for your own types. So they get stuck in that namespace so that you wouldn't notice them and you wouldn't use them. So this is not the most compelling example. But wait, the next one is. Because the very next example you come up with is pair. And you can't use a map without a pair. You can't do hardly anything without a pair. Notice that pair, the constructor, which might start making you think of our previous example, takes a reference to a const t1 and a reference to a const t2. And it requires copy constructability. So it spells out that what it's going to do is it's going to copy construct from x and y. So what? What does this imply? So if any t1 or t2 that you instantiate pair with, the copy constructor is not going to modify the bits of the source object, right? Or, what's the other way to be thread safe? Or it's internally synchronized somehow. Maybe it's got a mutex or something like that. That means any copyable type T that anyone that you write, anyone, not just you, if you ship it to others, could ever put into a std pair is required by the standard, no ifs, ands, or buts about it, to have thread-safe copying, where you are allowed to copy from the same object in multiple threads without any synchronization, and that had better work. So who was it who said you want that to work? You no longer have to tell them you want it. You can say the standard says so. We're just remembering this and discovering it. So you may have to go back and fix a couple of types. So what does this mean? So this is the change in C++11. Thread safe, again, means bitwise const, or you're going to do internal synchronization. So either way, you don't need external synchronization. The standard library guarantees that const means thread safe for all its own types and operations, and any operations it's specified to call on your types, which are quite a plenty. And you should just do it for all const operations, because as you already discovered at the back of the room, there are people who expect this, and you should too. Remember, this isn't, the fact that people expect this is not new. People have been expecting this for 25 years, and we've had to keep telling them, no, it's really not that way. It's this embarrassing thing that's sort of logically constant. I'll explain it to you over lunch one day, right? No more. It means, const means thread safe. And of course, if you actually declare a const object, a variable that says constant, where you declare it and define the object, then of course, it's always been illegal to cast away const from that. because if it's a constant, then, and it's global, the compiler has always been allowed to put that into read-only memory or something. And again, here, for many more reasons, any const object, you can't cast const away from safely because its operations are no longer guaranteed to be thread safe if that's a shared variable. So, the changed fact of life, by the way, you might have known we played David Bowie's Changes. There's a reason for that, intro to this. We used to say const means logically constant. It's kind of awkward, but we got over it, and that's what we taught people. The new reality is const means thread safe, either bitwise const or internally synchronized. This is a profound change. For many types, it'll be a very small change because you already probably coded that way most of the time. This is now fundamental to stay out of undefined behavior land in a newly concurrent and parallel world and a newly concurrent standard library. So half the talk in one slide is const means thread safe. Any questions about that before we go on to the second keyword that you don't know anymore? Yes. You're still, if you take the synchronization approach, so you're doing internal synchronization to make the const methods thread safe, then you might still end up encountering a certain other keyword. That's true. Hold that thought. Any other questions that don't involve keywords starting with M? Oh, all the hands went down, so let's proceed. Oh, one more question at the back. Is it possible to detect it at compilation time? Detect which? That something's const or not thread safe? In general, so how do I find out if my type is affected? If your type is doing, for instance, you've got a class with a copy constructor that's supposed to be reading from the source object only, make sure you take it by const reference. If you're doing that and you see any const casts in there, then that's a little trigger, a little red warning reminder. Sirens should be going off in your mind and all the coworkers around you should be fleeing for the exits. Or if you see a certain keyword starting with the word M, letter M, let's go to that. Thanks to Jim Park for this example, because this is the example that started getting me thinking on, wait a minute, const has really changed, because he was talking about how mutable was really so often a bad idea, even in C++ 98, and constantly had to tell people, really, most of the time you try to use it, those patterns are anti-patterns. There's only a few good uses, and even they're questionable. And as we were talking about this, we realized, wait a minute, this is different in C++ 98. And in particular, consider this example. Let's say you have a class widget, some or all of whose internal data structures may be protected by a mutex. Sometimes this is an appropriate pattern. Now, imagine you've got some sort of getInfo function, which is going to return some sort of info object, which I'm going to initialize using C++11 brace initialization, so I don't have to say temporary info paren anymore. I can just say that. Isn't that nice? I love C++11, I mean. I love C++11. And here, I'm going to read from all that more data that's protected by the mutex, construct the value, the info I want to return, and return. Now, of course, because I'm reading the shared state, I better take the lock on the mutex. So I have a lock guard to hold a lock on that mutex. And this code is exactly what you should be doing. But there's one thing that's wrong with it. What's wrong with it? It doesn't compile. Exactly. It won't compile. Other than that, it's perfectly good. Why won't it compile? Because inside this getInfo function, which is correctly const, we are trying to take a mutex lock. Well, guess what? We modify the mutex. We say, oh, this thread now owns it. We have to modify its state in order to take the lock. That's a modifying operation. Other threads may notice if they're trying to take the lock too. How would you solve this? Well, the traditional time-honored way is, especially if you're a Tom Hanks fan, is to play the Castaway game. And if you play Castaway, then you can simply add a const cast to a mutex ref. Remember the reference, it won't compile without, because mutex is a move-only type. And this will work. It will compile, it will run, it will even run correctly. What do you think of this solution? Run for the hills. Well, it's legal. You could probably find examples like this in Bjarne's book. You wouldn't criticize Bjarne, would you? You would. Okay, well, anyway. This side, let's have something from this side of the room. Anyone? What do you think of this solution? Yes? You hate polluting your code with const casts. I can agree. I understand. So looking at this, this solves the problem. But Yeah, it's tedious. It's more typing because I got to write const cast mutex rapid manually. The shift key is involved several times. That always causes carpal tunnel. And I have to do it every single place the mutex is used inside a const member function, right? So there are two jokes on Castaway. The first is, of course, you're casting away const RRR. Isn't that funny? But also, if you've seen the movie Castaway, you remember that after being on this desert island for a long time, Tom Hanks is finally rescued. His character is rescued. They bring him back to much cheering. They have a big event to welcome him home. And there's on the table this big pile of crab legs, very expensive. And he can't bear the sight of it because he's just been eating almost nothing but crab legs and fish for the last, I don't know how many years. Even if you can tolerate one crab leg, you will get tired of this crab leg after the first 1,000. So we don't want to be writing this all the time. Even if you don't mind it today, you will get sick of it, even though it's a really pretty kind of cast. Instead, we say, well, yeah, C++ has always had an answer for this, right? It's mutable. We should just say mutable mutex m. First of all, does this solve the problem? Yes. Yeah. See, I don't always ask trick questions. That's what keeps them guessing. So then you can sort of lure them in, the ones that are actually obvious. What do you think of this solution? It will compile. It's a step forward. It's a step forward. It always felt wrong to do mutable. Yes. And you know what? I agree with you on the old mutable, because it was always kind of cheating. Because you're kind of saying, well, this part isn't really const. Now, sometimes it was valid if you had, say, a counter inside the class that didn't affect the observable state of the class. But it always made you feel kind of icky because it seemed like you knew you were doing a right when maybe you were kind of sort of promising not to. And what about padding? But there was all sorts of questions. You can feel good about mutable now. I finally do. It's very liberating. Embrace it. Let's see why. This is a great solution, but there's something to be said about it. We'll come back to it in a second. So the quick quiz in classic C++ is, what does mutable mean? How would you define it in a phrase or a word or a short phrase? Teaching someone what does mutable mean. Sorry? Get out of jail free card for const. Okay, so that means it's logically const. Now, that's an interesting thing to be saying about, because that's how we define const, isn't it? Not observed by const, not observably non-const. I like all of these. We've taught a generation of C++ developers that mutable means logically const is another big one, which is exactly the same words we used for const. Or not observably non-const. If you can sort of squint and avoid seeing the double negative there, that's really what it amounted to, what we were saying. Don't worry about it. You can't tell because it doesn't participate in any kinds of side effects that are visible to the users of a type. If you know that about mutable, you don't know mutable, because it no longer means that in C++ 11. Mutexes, as we just saw in that code example, that are internal to a class want to be mutable. Why? What is the fundamental reason why they want to be mutable? Maintain the const guarantees? Because they're, say that loud and proud? Because they're already thread safe. They are synchronization objects. They are designed to be used without synchronization from other threads, because if you had to synchronize them, boy, we would be in a wonderful place, wouldn't we? Sisyphus had nothing on if we had to synchronize access to mutexes using. Yeah, you start losing words. It's because mutexes are already synchronized. That is why they naturally want to be mutable if they're class members in C++ 11. Question? So if you have a bunch of, I think what you said is you have a bunch of member variables that are mutable. Yeah, so you're doing instrumentation or something. If those variables, so if that type, the objects of that type, can never be used with the standard library, and that can call const functions on them that you could be changing these mutables on, and if they could ever be shared across threads, yes, you have to make them thread safe. Typically what you will do is take all the mutable variables you've got and make them non-mutable and put a mutex around them, or something like that. That's the kind of thing you would do, or keep them mutable. You want to encapsulate a mutex usually with the data that you're protecting with it, but that's exactly the kind of thing to look for. Because if you have existing code that says mutable and it's not an already synchronized object, so this is the anti-pattern to look for. If you see code that has a mutable class member that is not already thread safe, like it's not a message queue that's designed for thread safe use, it's not a mutex, it's not an atomic, that should not pass code review anymore. Because we used to teach mutable is not observably non-const, which was kind of awkward, but it was what we taught. Now it's much clearer. Mutable means thread safe too. It means bitwise const, or in the case of something like mutex, already internally synchronized. This is a profound change. However, you might have noticed that because of the way I chose to phrase the description of mutable, it still holds, because const now means thread safe. So not observably non-const means not observably thread unsafe, which means thread safe. It's actually consistent. It's like somebody was designing the language for this back in 1979. So remember the option 2 code we saw, where we make the mutex mutable, which now we know means thread safe. What's this mutable really saying? The most natural way to express a member that is thread safe and therefore gets a free pass on const, which means thread safe. Like, don't worry about this. This one's already thread safe. It gets a free pass on thread safety, which we spell using const now in C++11. And it's the same as before. It's always meant as good as const or logically const. Here's another example. Let's say I have an atomic counter, and I'm trying to update it in a const member function. Let's say this doesn't change the observable state of an object. Because it's atomic, and because it's const in there, I can't update it. It won't compile. Because it's atomic, however, I can make it mutable. The counter is thread safe, right? Therefore, it wants to be mutable so that you can use it in a non-const function. If you forget to say mutable here for this thread safe member, your compiler will tell you. And what will it write? Write const cast, which is now thread safe cast, or make it mutable. The error messages already tell you the right thing to do, which is kind of a nice compatibility story. Watch for 4 more examples in my concurrency talk on Wednesday. I did not intend to write them. They just come up because it's the way that you need to write them. We'll have a member that's a mutex. We just saw why it wants to be mutable. We'll have a member that's a concurrent queue. We'll see why it just wants to be mutable. And then the code is clean as could be. So the talk in one slide is the news in C++11 that very few people in the world understand, including, as far as I know, the people I've asked on the standards committee were not really aware that we had quite gone and actually done this. We talked about it, but that we'd actually done it. Because we didn't do it in section 1.10 in the language, but by doing it in the library and all types used by the library, that was just about as good. And we might as well go back and add that one little word in section 110 as well. Const means the same thing as mutable. It means thread safe, which means bitwise const or internally synchronized in C++11. So that was the technical secret. Wasn't it much more fun to discover that live? You'll get the handouts afterwards, but I sort of withheld the handouts because there's a sort of fun in group discovery, is that we've now gone through an experience together. It's character building or team building or something, and we're not likely to forget it. So remember const, mutable, and I like that several of you are already thinking, oh, what about certain code back at the ranch? So look for const casts that shouldn't be there, because now you know that that really means thread safe cast. Look for mutable members that are not synchronized types, that are not thread safe, like atomic or mutex or concurrent queue. Those should not pass code review anymore, and you'll probably want to do that, go back and fix them. The good news is most people didn't use mutable anyway. Now it actually has a really practical use that is actually well aligned with the use it's always had, now that we finally got around from our wishy-washiness about const to say, no, const really does mean bitwise const, or synchronized, or as good as because of synchronization. Having said that, we're now going to take a switch, a context switch, to, as you'll see in your schedules, to a completely different kind of talk. Any last questions about const and mutable before we go to that? So what I heard of that is your concern about the casting away const from a really const object is undefined behavior. Is it about that? And how does the compiler know? Well, today the compiler doesn't really know that either. I mean, you might get a few compilers who may warn you about it if they can see the original definition. You're doing a const cast on the actual variable. and it's a global scope or something. But usually by then you've passed it through a function or two as a const ref and you don't know anymore, right? The mutable keyword is not going to do anything to change object layouts. It's not going to do anything to change code generation. The best it may do, including as with constcast, is the quality of diagnostics if you write something that's in undefined behavior land. Because now you're saying, hey, look, I want to actually treat this as const, right? Whereas before, if you just cast const away as mutable, it just lets undefined behavior, but how's the compiler going to diagnose that? The program might do what you expected. That's a possible undefined behavior, unfortunately, which makes undefined behavior so evil to track down. So at best, it'll help you with the quality of diagnostics because you're declaring your intent, but it has much more of a purpose now. It now has something much more valid to declare. Because, sort of logically const, or get a free pass on const was kind of a fuzzy concept when const itself was kind of fuzzy. But thread safe, hey, we know that. And we know how important that is today.